Labas vakaras, sveiki visi susirinkę. Aš taip lietuviškai pradėsiu, pasakysiu porą žodžių, o po to angliškai, nes mūsų šio vakaro darbo kalba ir šitos serijos, paskaitų serijos darbo kalba yra anglų kalba. Tai dar kartą labas vakaras visiems susirinkusiems ir susirinkusioms. Malonu Jūs matyti, atėjusios į antrą iš ZOOETICS paskaitų seriją. Ir kadangi čia mes susirinkome Kauno technologijų universitete, o kaip žinote, technologijose labai yra svarbu laikas, tikslumas ir protokolai, tai aš jums leidus pasinaudosiu šituo popierium ir pradėsiu angliškai. Hello, my name is Gediminas Urbonas. I'm artist and associate professor at MIT program in art, culture and technology. Thank you very much for coming to the second in the series of ZOOETICS lectures in which we are seeking to unpack, re-evaluate and recombine notions of Anthropocene, nature and interspecies. ZOOETICS combines the three notions of non-human life, human life, and knowledge and poetics. Politics and poetics, well, you know, that's slippery. Non-human life is signified by our site next door to Kaunas Zoo. Human life and knowledge are signified by the university. At this moment, specifically, Kaunas University of Technology. And poetics in this project conjures fictive imaginings and language play that can help us move into a future reconnecting non-human life and human life. Thanks to our partner, KTU, for their effort, and especially to Asta Punzene, Vice Rector, and Violeta Kauneliene, and the research groups at KTU joining this transdisciplinary initiative. Thanks to MITA, Agency for Science, Innovation and Technology, Lithuanian Cultural Council, and European Union Frontiers in Retreat project for financial support. Last but not the least, thank you my partner Nomedo Urbonas and Victoria Šiaulytė, a research scientist at UTempus Interdisciplinary Art Program. Podcast of the lectures will be on our website, zoetics.net. We invite you to interact with the project as it develops through our online reading group. You can also ask questions on Twitter. Use #ZOOETICS for that. In format for this session is that we will have 45-minute lecture from our first speaker, Skylar Tibbits, and Skylar will take 2 questions from the audience at the end of his talk. Then we will have a 45-minute lecture from our second speaker, Calebas Harperis, and Caleb will similarly take just 2 questions at the end of his talk. Then we will have 20 minutes for panel discussion between the 2 speakers, you, the audience, myself, and moderator of the panel, my ZOOETICS colleague, Dr. Tracy Ware, who is a research scientist at Oxford Brookes University in UK. Tracy will moderate questions after the lectures and during the panel. The lectures and panel will be in English, since there were a lot of requests and questions and little time last week. We are extending the session to run until 8:30 p.m. I would also remind you to please turn off your cell phones, mobile devices, and other devices that may make some sound tonight in order to respect our speakers and your colleagues in this room. Thank you. So I'm delighted to welcome Skylar Tibbits, who directs MIT's Self-Assembly Lab, which is developing self-assembly and programmable material technologies for new manufacturing products and construction processes. The self-assembly research will enable breakthroughs across every applications of biology, material science, software, robotics, manufacturing, transportation, infrastructure, construction, the arts, and even space exploration. Skylar's accolades include the Architectural League Prize, the Next Idea Award at Ars Electronica, the Visionary Innovation Award at the Manufacturing Leadership Summit, the TED Senior Fellowship, and being named a revolutionary mind in Seed magazine. Please join me in welcoming Skylar Tibbits.
Hear me? Yep, we good? Thanks so much for the introduction and invitation to be here. It's really a pleasure. Hopefully this doesn't make too much noise. So as you heard, I run the self-assembly lab at MIT, and we're housed in the architecture department. And I actually came to MIT from a background in architecture and then studied computer science. So I really look at the lab as a convergence between design, the physical world, and computing. If we look specifically at what software and computer science brought us, it's no question that computation radically changed the way we make things. It's no question that computation changed how we design, what we can design, and changed the process of design, whether that's geometry, or that's evolutionary solvers, or that's simulation, etc. Maybe I should change this. Do you have the handheld mic? This is super loud. Is this better? We good? Okay. So software and computation radically changed how we design. As a student and then as faculty, it's no question that was a game changer. But it's also no question that code, when it's linked to machines, radically changes how we make things. Digital fabrication revolutionizes how we can produce, what we can produce, the materials we can produce with. You could replace this video, which is a multi-material printer, you could replace that with a laser cutter, a CNC router, water jet, etc. So the first is code for design, the second is code for machines, and what the lab looks at is how we bring code to materials. How we can program materials to change shape, change property, assemble themselves, and have all of the capabilities that our software world has, but bring that to the physical world, bring that to material science. After that, we think we're going to look at code for construction and how we can rethink construction, manufacturing, product assembly. And rather than forcing lots and lots of energy into materials, these brute force techniques to assemble things, what we're interested in doing is embedding more information in the materials themselves so that they can collaborate with people, they can collaborate with machines, and assemble themselves. So we're interested in thinking about assembly not from a top-down perspective, but from a bottom-up perspective. So the title of the lab is Self-Assembly Lab. It's a process by which disordered parts build an ordered structure through local interaction. Not human assembly, not machine assembly, but rather the parts interact with themselves to build higher order or more precise structures, for example. If you look at every other process outside of the human scale, if you look at biology, chemistry, material science, astrophysics, for example, all of these processes have components that interact with one another. They're subject to energy from their environment, they have interactive forces, and they assemble higher ordered structures. So there's no top-down control saying you need to assemble in this way, planet, or two cells need to be forced together to make this structure, but rather they have logic embedded in them. And we're interested in translating that to something we can use at the human scale, because the human scale predominantly is top-down. And we've become really good at that. If you look at buildings, if you look at furniture, you look at anything that we build at the human scale, we've become super good at forcing materials into place and doing what we tell them to do. So we're looking at another opportunity, and I think the most clear demonstration of that is a project that we did a couple of years ago with a molecular biologist and with a software company, Autodesk. And we looked at biomolecular self-assembly, specifically the poliovirus. So in this flask is the poliovirus. If you shake it hard, the parts break, and then you shake it randomly, but a little bit softer, and the parts come back together. And this shows all of the ingredients that we need for self-assembly. It has geometry and materials, which guide the final structure. It has local interaction, which is the error correction. So if two parts assemble in the wrong way, they break off. And it has energy and an environment. And so by designing around those ingredients, we can promote structures to assemble themselves into very precise and repetitive or regular scenarios. In this case, we looked at something called chirality. So chirality is right-handedness and left-handedness in biological systems. So we dump a bunch of black and yellow parts into the flask. You shake them randomly, and you always will get fully black and fully yellow. You'll never get half and half. You'll never get a soccer ball, etc. It'll always separate themselves. And the way that we do that is through local interaction. So there's different patterns of interaction on each one. So positive, positive, or negative, positive, negative. And if they connect in the wrong way, they will be upside down. But no third part will ever be able to bridge those two. So you'll have a weak local interaction, which means that as you shake it, it'll break apart. So it'll assemble, break, assemble, and break. If two connect in the right way, then a third part will connect, which bridges it, and it starts to get stronger and stronger and stronger. So you're guiding successful structures, and you're weeding out errors. And that way we can promote useful and precise structures, or self-sorting, for example. And I would look at that work as pure self-assembly, parts coming together to build a precise thing. But there's another category that we're interested in, which is self-organization. So the difference is that self-organization is more like solid liquid gas, or crystals, for example, where you have a bunch of components. So you have these fundamental modules, and by subjecting them to energy, they might form themselves into different patterns. They might, if you have a lot of heat, for example, they might move to a gas-like state. If you lower the temperature, it might move to an ice-like state or a solid state. And their interactions don't necessarily change. The components don't necessarily change, but they can produce drastically different global structures and material behaviors. So we started to look at carbon, for example, and how carbon can produce different geometries, different global structures, like graphene or graphite. It can produce linear strands, hexagons, pentagons, two-dimensional structures, three-dimensional structures. And this is the first time that we started to go to fluids. So we have this is a 200-gallon tank of water. We can control the turbulence in the system. So we have pumps that we can place in there, and we can play out different patterns. We can blast the energy, which is a sort of like increasing the temperature. We can lower the energy. We can create patterns, repetitive patterns, chaotic patterns, etc. And we study the different patterns that emerge. The local patterns like strands, like hexagons, pentagons. We study the global patterns like clumps or lattices or broken apart individual elements. But from this work, we then tried to go more into crystalline lattices. So this is a 500-gallon tank of water that we have in the lab. And we throw a number of units in here. I think there's 64 in this video. And we've recently gone up to 125. And again, we have control over the turbulence. So we can create different patterns. We can create vortex patterns. We can create linear flow. We can create chaotic patterns. And each one of these elements is neutrally buoyant. So we film this overnight with a very low amount of energy. And you'll see over time that all of the modules come together and crystallize or anneal into this precise cubic lattice. And so very different from the previous examples where you have a bunch of components that will always build the same thing. In this example, all of the components will always build the same structure. So you'll always get a cubic lattice, and in our case, very homogeneous cubic lattice without errors in the inside. But you can never guarantee the global structure, at least in this condition. So it's an interesting growth and accumulation rather than, let's say, a repetitive structure. One way to start to control that exterior, there's a few different ideas. One is that you can change the environment. So you can change the chamber. It's just like if you grow a crystal in a petri dish, it'll grow to the boundary of its chamber. Another way to do it is that you grow much larger than you would ever need and you shave off. So you have a mass of material. And then even a third way is that you can create a vortex, for example, and grow a tower or if you create a linear flow, you might grow a sheet. And a lot of these techniques are actually being used in new research in material science to promote new particle formations, for example. So a third category of assembly is what we call differentiated structures. So in this case, we dump in a bunch of units, and every unit is different. So in the previous two examples, every unit was the same. In this example, every unit is different. And it has only one place that it can find in the local structure or the global structure. So meaning it has to find that one position, otherwise it won't connect, it'll break off. And you can see we build this arbitrarily hilarious chair from these objects. And it's not that we're interested necessarily in proposing this as the future of producing chairs, although maybe it could be, but rather a chair is this arbitrarily complex thing where every component is actually different than every other component. In this case, we can now draw a wireframe shape, whether that's text, whether that's furniture, whether that's larger structures. And then every piece has its own final place. And just by interacting with its environment, it can then find that place and assemble the structure for us. And so we're interested in all three of these categories: precise repetitive structures, growth and crystallization, and differentiated hierarchical structures. And I consider this work on the basic side of our research. So we have a spectrum from basic research to applied research. On the basic side of the research, the goal from the lab's point of view is to understand these complex systems, to understand the phenomenon, try to invent new techniques, invent new capabilities, and try to push scalability. Maybe find where we could use this, try to find new capabilities like differentiation. How complex of a structure can we propose? Because there's an interesting spectrum from chaos to order. You know, if you throw a bunch of parts on the ground or you throw a bunch of parts in a chamber, it's very easy to get arbitrary random structures. That's more or less what happens every time you throw something together. But then it's also fairly easy to get very, very regular structures. So what we're interested in is trying to find a way to have control over the precision of the structure, have control over the complexity of the structure, but probably not be at either one of those ends of the spectrum, chaos to pure order. We then went to a much larger scale, and I'll play this video and then talk about it in a little bit. So this is the largest structure that we've done, and there's a lot more research going into this. Obviously, it's similar to the second scenario, which is crystallization and growth. You have a bunch of components. They're all the same. They move around in a fluid environment, in this case, the air, and they assemble very large lattice structures. We threw a bunch of parties, and people would throw them in the air like a concert. We had huge fans, and they would aggregate. And similar to the chair, you could look at this in a very pragmatic stance and say, okay, we're building large structures, and the application we're interested in is building space frame structures, but not using the ground as construction, but rather using the air as construction. So you assemble these things in the air, and as the helium dies, and each one of these is a 36-inch diameter weather balloon, as the helium dies, then you're left with this large lattice space frame. But when the helium's in there, you can lift a 10-foot by 10-foot by 10-foot cube with your fingertips, and then it becomes much more rigid and strong when the helium's gone. You know, on the other side, though, we're interested in what types of structures emerge, and every time we change the environment, we study fluid environments, we study aerial and fan-based environments, and gravity tumblers, and all these different scenarios, everything changes. Every time you change the scale, everything changes. Every time you change the components, everything changes. And so what we're trying to build is a science around this complexity of assembly. And most people will say, well, then that's not a very good method of manufacturing if it's so complex. But I think if we look at other domains, and specifically I like to point towards cooking, baking, or gardening, for example, there's really interesting analogies to how we can build very precise, very repetitive things. Let's say a cook, for example, the only thing they have control over is the ingredients and the energy. They really don't have any control over the molecular interaction or the local interaction. But what they're doing is collaborating with materials and collaborating with energy to produce results. And if you look at industrial food processing, we've become very, very good at building the same thing over and over and over again. You could take McDonald's, for example. But we've also become very, very good at master chefs who can collaborate with these ingredients and build one-off pieces. So there's an interesting analogy to manufacturing, where in manufacturing we try to control every single step along the way to try to produce more precise things, instead of collaborating with energy and materials. And so that's our dream for this scenario. So that one, sorry. That's our dream for this scenario, that we can rethink manufacturing, whether that's very large scale or very small scale, and produce results that we couldn't have produced if we had control over every step of the process. We actually let a collaboration emerge with those materials. Because if you look at a collaboration and your partner brings everything to the table that you bring, or they bring everything you knew about before, that's a really bad collaboration. So what we really want to do is have materials bring things we couldn't have done. The other category of research that we look at in the lab is called programmable materials or programmable matter. And the idea here is that you want to take materials that come in fixed shapes, quantities, sizes like sheets, fibers, bars, strands, etc. And we want to program them to store information, make local decisions, change shape, change appearance, change functional property. And the way that we do that is with a couple ingredients. On the top left is the materials and geometry. So this is the obvious one. Everything we build today has materials, everything has geometry. We're specifically interested in the material properties. So every material responds to energy. For example, wood responds to moisture, metal responds to heat, plastics respond to all sorts of things. But the geometry is how you can control that response. The amount of material you put might increase the force, or it might change the amount of time it takes to respond. If you put it thicker or wider, or you change the grain direction, etc., you're changing the mechanical behavior. So we're interested in the mechanics to promote useful transformation. For example, if you want a linear actuator, or you want a winding mechanism, you want something that expands, that shrinks, that folds, that curls, all of these mechanical transformations become useful in industrial applications. So if you want flaps on an airplane, for example, you might want some rotary motion. And you're trying to figure out how you can make a material do that on its own. And the way that we activate it is through energy. We're specifically interested in passive forms of energy because there's this opportunity around us to utilize energy that we don't normally utilize, whether that's sound or light or heat or moisture. These are forms of energy that can create highly active materials that we traditionally don't use. We traditionally look at it in terms of robotics, and we use power and batteries and fuel and those types of energy sources to get things to move and to transform and to sense. And we're interested in trying to produce new materials that can respond to passive energy sources. This work is on the applied spectrum. So most of the work is trying to develop new materials for industrial applications. I would say this is probably our most radical or basic of those, and it'll move to more applied. This work is work where we developed a way to print DNA, and we print DNA as a sensor. So in this case, we're using a software to be able to understand the biological information, so the ACTG of DNA and what it's going to bind with. So essentially like Photoshop for DNA. And then we developed a number of hardware tools to print DNA. So literally this is just inkjet printing DNA. And we print it on nitrocellulose paper. So in this case, you have one strand of DNA on the paper, and when we wash with a complementary strand that has a gold nanoparticle, the letters MIT show up. It's a little bit dark. So the idea is that just like a pregnancy test or just like a blood test, you can actually print things on paper, and only when it meets the complementary thing, an image will show up. So we worked with BioLab, the Little Devices Lab, and the Gherke Lab, and software companies. We worked with all different people, and everyone saw something different in this. The bio folks see this as universal diagnostics, that anywhere in the world you can have a desktop 2D paper printer, and you can print out a custom diagnostic. If you want to know if you have dengue or malaria or AIDS, you can print it on a piece of paper, wash across it with a blood sample, and if you have malaria, a mosquito will show up, for example. So you can make your own diagnostic that aren't super expensive, they're totally customizable, and we can have images that transform. As a designer, I was interested in how we can use these as smart ink or magic ink, for example. How can we use biological material as a programmable ink that changes based on its environment? So we took the Game of Life, which is a computer science program. Essentially, it's logic of pixels. We started out with the letters MIT, and we got these abstract patterns on the bottom right, and we printed those with DNA. So the idea here is sort of like the Harry Potter book, that you'd have a piece of paper or clothing or packaging, and the ink on that packaging or in your clothing is changing based on the sunlight, based on air pollution, based on the proteins from your skin. So those images are transforming and telling you something about it. If it's packaging, for example, it could be on the outside of a food package, let's say, and it might say, this food has been exposed to this amount of temperature or this sunlight, so you probably don't want to eat it. So the packaging can become smart and tell us something about the internal and external environment. Our most notable work from the lab is something called 4D printing. And the idea was that we wanted to take 3D printing and add the element of time. So that's why we said 4D, that we wanted to take it to the fourth dimension. Essentially, it's like printing smart materials. So smart materials are materials that you can activate, and they usually change shape or they change length. The problem, though, is that they're fairly niche. They're fairly expensive. They come in fixed shapes and sizes, like fibers and sheets, and they have fixed properties. So if you want to embed them in your clothes, if you want to make smart clothing, you have to assemble it in there. You have to give it power. You have to give it just the right conditions, and it's fairly complex. It's also like robots and printing robots. So robots are great, but they take lots of mechanisms, they take lots of material, they tend to be failure prone, and they're hard to assemble. So if you look at apparel, fashion, and shoes, for example, they've wanted smart materials and smart clothing, smart shoes forever. But the real problem is that it costs more money to assemble, the components are more expensive, they fail all the time, and then there's this huge power issue. We don't want tons of power in your shoes, for example. So how could we use multi-material printing as a way to activate and program materials to transform? So we started working with Stratasys and Autodesk. Stratasys is one of the leaders in 3D printing. We use their multi-material printer. In this video, you're seeing two different materials printed at the same time. One of those materials is a rigid plastic. And to me, that is like the braille of our system. That's the geometric information. It's the backbone, it's the joints, it's the precision, the mechanisms that we want. So if we want it to fold, we can print different mechanisms if we want a precise angle, etc. And then the other material is an expanding polymer, and it expands 150% when it meets moisture. And that gets you the energy to go from one state to another state. So we have all of the information, geometries, material, and energy. And we've shown that we can go from any one state to any other state with precise control of folding, curling, stretching, all of those mechanisms that I talked about before. One of the major challenges is if I want a chair to go from its original state as a table to a chair, let's say, or a chair to turn into a cup, that's a crazy world. How do you figure out how to do that? And so that makes us think that we need new design tools and we need new fabrication tools. We've done a lot of work on simulating that, and I would say that we're just getting over the low-hanging fruit, which is if I have an object, what can I simulate that it will transform into, and when I print it, will it do that? And I think we've shown success in demonstrating what we can fabricate, we can simulate. But the next step is, if I want some really arbitrary shape, what pattern should I print to get there? And try to propose new design solutions that will get me transformations that I couldn't have preconceived. And that's sort of like the protein folding problem. How do you go from an arbitrary strand into a complex 3D object? So this is one of our first demonstrations that we did. It's a single strand. You can see the two different materials, and when it's dipped into water, it spells the letters MIT. And we showed here that every angle is the same, so it's just 90 degrees, but we can precisely control where it folds in 90 degrees, positive or negative, etc. And we can go from a strand into a two-dimensional sheet. And then we started to go from two-dimensional sheets into three-dimensional objects. The interest here is that if you print a two-dimensional sheet, you can minimize the material, you can minimize the time for printing and support material, etc. But then you can ship it, minimize the volume, and it can transform on the other side. So most people will say, well, I want to print a huge object. I only have a printer that has a small bed size. How do I print that object? So the interest is that you can print small things that transform into much larger objects. Not to mention time. Printing big things takes a lot of time on today's 3D printers. So you go from a flat sheet into a precise three-dimensional structure. And we've tried tons of different strands that go from text to other text, straight lines, self-folding proteins, flat sheets into polyhedra. In this case, we worked with Eric Demain, who's a computer scientist and origami master and mathematician. And we looked at curved crease folding. So there's a category of problems, which is how do you go from a flat sheet into double curvature? And double curvature is a complex thing and interesting for the apparel industry and aviation and building materials. Essentially, you have a flat sheet of rigid material. How can you make it curve? And normally, we've put a lot of energy into that, forming it and forcing it into place, or building molds and vacuum forming it, or tailoring it, for example. And curved crease origami utilizes the techniques of origami, but shows that you can create saddle curvature from flat sheets. And then we went a step further, and we showed that local stretching can produce arbitrary but precise curvature. So if you have a flat sheet and you expand and contract in very precise ways along that sheet, then you can promote it to transform in positive and negative curvature in any shape that you want, simply by expanding and contracting. So you produce a flat sheet just like every other flat sheet, but we can then propose that it transforms predictably locally to make global transformation. Something we've been interested since then is instead of discrete joints and mechanisms, which is sort of like an older school mentality of engineering, can we have more continuous material deposition? So if we print with a flat disk that has a gradient distribution of materials on the left, we can then propose different structures to emerge. The bottom are photographs, the top is a simulation. But interesting here is that it doesn't always go from a standard printed structure into a precise object that you've proposed. But rather, we're saying, can the material give us a new solution based on the amount of time it's subjected to the energy source? So we print a flat sheet. If you dip it in water for an hour, you get the middle one. If it's 24 hours, you get the one to the right. So you get different solutions depending on how much energy is subject, or how much time, essentially, that it's in that environment. And therefore, you can think about this as imagine that you have a product that can transform itself to give you a more optimal structure based on the environment. So it doesn't wait for you to say, turn yourself into this new product because that's better, because I know that it's better. It's going to say, no, I'm going to find the better solution, and I'll transform myself into that based on the environment. And after we put out the work on 4D printing, a lot of people came to us, specifically companies in many different industries, and they were super excited about it, but they said, you know, we really don't care about crappy plastics. So what can you do with everyday materials? What can you do with materials that we already use? And how can we program materials that aren't just niche 3D printed plastics, but everyday industrial materials? So we've developed a suite of materials that we're calling programmable materials. These materials can program, we can program them, and they can transform in shape and property like you saw in the 4D printing work, but they're using traditional materials, or let's say new compositions of materials. And we've developed an amazing team of collaborators for this. We've worked with product designers like Christoph Kuberin, Eric Demain, mathematician, computer scientist, material suppliers, and software companies to create a sort of a whole workflow. So as I talked about before, one of the major challenges today is actually the design tools, not even the materials. And so we've tried to create a workflow where you could simulate the material properties to transform in predictable ways, but rather that it's we wanted to expand it beyond the 4D printing simulation. So in the 4D printing work, it's very specific to that material. But now if we can make any material programmable, how do we have a universal design tool? And so we found a very simple way to have geometric transformations simulated and then output files that we can print, which will then predictably transform in ways that we wanted. We developed so far 3 different material palettes, let's say, and we're developing more as we speak. One of those is composites, specifically programmable carbon fiber, textiles, and wood. And wood is an interesting case study because we've had transformable wood forever. Wood naturally transforms, and we've been using it in precise ways for manufacturing products for a long time. You can go to Japanese joinery where you have wood in a controlled environment based on humidity. You put it into the hole in the connection, and then it swells to become permanent, fixed, precise. You can look at Eames furniture where they add moisture to the wood and then form it. And they get chairs. And even more contemporary researchers like Aki Menges in the University of Stuttgart, who uses wood veneer, and based on the aggregation of the grain pattern, you can have predictable transformations. But the problem here is there's 2 problems. One is on the manufacturing side. If you look at Eames furniture, there's lots and lots of energy that goes into taking a flat sheet of wood and transforming it into a complex shape like a chair, whether those are steam chambers or molding or physical force. And then on the right-hand side, although we don't have that same physical force, we're constrained by the grain. So for example, if I wanted to find a piece of wood that folds into the letters MIT, I have to go to a forest and find a tree that has the letters MIT in it, which is never going to happen. So the question is, how can we use the behavior of wood but have the universality of our printed materials? So what we've done is actually print with wood, and we print this wood in any grain pattern that we want. So we can change the density of wood, we can create diverging grains, we can create curved grains, we can create meshes, anything you can imagine in terms of wood grain. And so the way that we do this is we have a filament extruder. We actually create our own filaments. It's a mixture of wood particles and plastic. You can control the amount of plastic, the amount of wood, the type of plastic, for example. And then you print your own grain. In this case, you're seeing linear grain. You can create a 3-dimensional composite, and then we subject it to moisture or water. Depending on how much moisture it is in the environment or in the chamber, you get different results, and also depending on the grain direction. So here you're seeing the same sample with 2 different grain directions behaving in very different ways. We then went to folding, so from curling to 90-degree angles and positive and negative curvature, and even things like fish scales or strange shapes that would never happen in wood. We can produce this curling behavior and have diverging, converging wood grain patterns. We then had a nod to the Eames family. Eames is very famous for doing this children's furniture, but instead we were proposing that we would have flat sheets that self-fold into the children's furniture, in this case the elephant. In terms of textiles, the interest is that you want textiles to transform predictably on their own. And there's 2 categories here that we've researched. In the video, you're seeing the first category, which is pre-stressing. And this is a technique used in a lot of different industries, like concrete, for example. So we pre-stress it, and then we add constraints. So here we're printing on top different patterns that have thickness, grain direction, width, material properties, etc., which then promotes it to transform when you release that stress. You can laminate it, you can inject it, etc. But depending on the material and the pattern you've designed, it'll jump into shape. So that's a minimal surface hyperbolic structure. You can create different mechanical features. You can create pleating, which is interesting techniques, different stitch patterns, etc. So we're interested in textiles as a new active material. The other category which we're working on now is that you print active material so that those textiles can repeatedly transform over and over and over again without the pre-stressing. And the last material that we've released so far is our composites work. And we've worked with a company called Carbotex. They make the world's only flexible carbon fiber. So carbon fiber is known for light, super strong material. And they make actually a fully cured but flexible material. And they can CNC spot where it's flexible, where it's rigid. And then we print active materials on and within that, and we impregnate those materials so that we can create mechanical transformation. And so it repeatably transforms over and over and over again. And we've shown 3 different activation energies: heat, light, and moisture. In this case, you're seeing heat. And it's very fast and completely repeatable. So it has interesting properties similar to what we saw in the 4D printing work, but now with a super light, strong industrial material. So from that work, a number of companies came to us. In this case, Airbus said, this is great. Can we use it for flaps and vents on planes? And they had this challenge. There's a component on the top of the plane called the air inlet on the top of this engine. And it basically sucks in cold air to cool the engine. But the problem is that as you're flying, it causes drag. So the aviation industry would normally put in actuators, sensors, electronics, and have this mechanical flap that opens and closes. But it causes a lot of weight. It has failure mechanisms. And then they have to put control mechanisms in the cockpit, which then stops production and all these other things. So really what they want is a dream material that is a single layer thick piece of carbon fiber, which is what you're seeing in the video, that can open and close precisely but autonomously. So there's no external actuators, no external electronics, sensors, etc. It can autonomously control the airflow into the engine, either based on temperature, which you're seeing now, or based on altitude and differential pressure, which is what we're developing. Another company, kind of in a similar vein, came to us. This is BAC, Briggs Automotive Company. They make one of the world's fastest street-legal supercars. So think about race cars, Formula One, or sports cars. And forever they've had adaptive aerodynamics, or maybe not forever, but for a long time they've had adaptive aerodynamics. But it's a similar thing. They use pistons and hydraulics and massive actuators, which add tons of weight. And the worst thing you want to do if you have a race car is add weight to your car. But they also have all these control mechanisms and electronics. So what we're developing is a rear wing. And this rear wing can open and close to control aerodynamics on the fly. This is one of our early prototypes. So you have a rear wing. The scenario is that, let's say it's a sports car. If it's raining, what you want to do is you want to decrease aerodynamics, which basically causes drag. So the airflow pushes against the wing, creates drag, and then pushes down on the rear tires. So you increase traction. And then when it dries out, the wing can then close. And you can do that anywhere on the car, so you have this tunable aerodynamics. And similarly, you can control heat flow to the engine, like we showed with Airbus, for example. So where do I think this stuff is going? I think there's 2 main categories, at least, that are particularly interesting for us. There's lots and lots of industry applications. There's lots and lots of research to still be done in terms of basic science. But I think there's 2 categories of really radical shift that we could see. One is a future model of fabrication or manufacturing. And the idea here is that if you look at our traditional means of fabrication, for example, or even more contemporary ones like printing, CNC milling, routing, water jets, etc. The problem is that you send a file to these machines, let's say it's a printer, and you, in the best case, get a slightly worse version of what you send. So you send this pure, perfect geometry, and you'll never get that pure, perfect thing out. You're always going to get a slightly worse. But even in the best case, maybe you could get the same. You're never going to get a better solution than you gave it. And so what we're interested in is trying to collaborate with materials and machines so that when I send a file to a machine, that machine can give me a better result than I could have ever dreamed of. And that would be a nice collaboration, because we could say, hey, I want this flap, or I want this bracket for a plane, but I want you to tell me what a better bracket is than I could ever conceive of. And the way that we think that is possible is because materials can be reconfiguring themselves, like you saw in a lot of the first projects. They can be reconfiguring themselves into more comfortable states. An example that I didn't show is we have these huge fans, and we assemble structures, lightweight structures on top of the fan. And what we noticed was that what started to emerge were these parachute-like shapes, because as the fans are blowing, anything that's a single module will eventually come back down. Anything that doesn't fly very well will slam to the ground and break apart. And the only thing that ever lives in this kind of evolutionary setting is parachutes or wings or things that fly because they stay up in the air and they don't come down. And so in that sense, the material can reconfigure itself into an optimal or comfortable state, something that minimizes the energy and produces comfortable results. But we don't only want to stay in that material realm, because if you think about it as an energy landscape, you might be in a local minimum. You might not find the globally best solution. You might find a local best solution. So what we want to do at the same time is track what's happening, control the energy in the environment, and simulate what is possible to happen. So say these structures are emerging into a parachute. That's really good, but it could be this other type of parachute if it continued, if we just change the energy a little bit. So we can actually kind of dance with the materials and the energy to produce these structures that could have never been preconceived. And the materials reconfigure themselves into new optimal structures. So we think about that as a new manufacturing application, a new fabrication application. And the other big category, I think, is more general and more applicable. Almost every industry is interested in robotics, whether that's manufacturing, and they will say the holy grail of the future of manufacturing is better and better industrial robots that are higher precision, lower energy, need less programming, etc., more versatile. So almost everyone in industrial manufacturing is looking at robotics. Then there's a category of applications like planes, like cars, like boats, that already use robotic actuation or electromechanical actuation. And then there's another category like fashion, textile, shoes, which are industries that would love to use robotics but can't because they're too expensive and failure prone and all those kind of things. And so all of those industries, I think, are transitioning into a different form of a robot. Not a robot that's super hard, made out of metal with motors and electronics and all this kind of stuff. That's our old school robot. Almost everyone that I know in robotics is shifting to softer, more material, pneumatic, adaptive, flexible, transformative materials. And we're proposing that these materials can have all of the capabilities that our other robots had, whether that's logic, decision making based on their environment, actuation, sensing, etc. And these new materials that have robotic capabilities are just as cheap as traditional materials. They're easier to produce. They're easy, or they do self-assemble, or they're easier to assemble into them because they're already made out of the materials that our textiles and our shoes are made out of. And they're easy to control because they're collaborating with us and they're responding to the environment rather than just listening to our demands. So I'll leave you with a quote that I think kind of sums up our vision and where we think we are. We believe that it's now entirely possible to program nearly every material to assemble itself and transform in useful ways. And I'll quickly show a vision or an image of our lab and invite anyone to come visit us if you're at MIT. We have crazy tanks and concrete mixers and fans and balloon parties and weird stuff like that. So I'll leave it there. Thanks so much.
Skylar, you mentioned briefly types of... Oh, okay, yes.
What the class I was late. So we were thinking about applications. Maybe you have told, but I'm just wondering, have you explored the broad application as health technology, as prosthetics, or any other applications?
Yeah, so the question, if you couldn't hear in the back, was applications for health and medical devices, et cetera. And it's a great point. And actually, the medical industry is, to my knowledge, the first industry that adapted smart materials. And you can look at a stent, for example, for arteries as a great example of that, which uses nitinol, a shape memory metal. And so they're kind of early adopters. And they have this interesting challenge if you look at surgery, that you really want to do stuff on the inside, but you can't get there, and it's too small, and it's hard to control. So we kind of want to deploy autonomous materials that will expand, contract, tunnel their way through. And so the answer is yes, a lot of people have come to us and they're super excited and they get it right away. They're like, look, we've been doing this for a while, we get it. Can we have materials that do X, Y, and Z? And I think there's lots and lots of applications. The other interesting one is orthodontics, for example. Invisalign is the I think, the first company who's used printing. And so basically it's like these trays on your teeth, for anyone who doesn't know, and basically they move your teeth tray by tray. So instead of having braces and tightening these things, you can move them tray by tray, and there's a lot of interest in doing a self-transforming tray. And so for sure, there's definitely a lot of work to be done in like smart devices and diagnostics, like I showed with DNA printing. But the other one is like drugs and drug discovery and drug delivery. There's been a lot of work at nano to micro scales on how you produce new drugs, discover new drugs, or even have DNA capsules. And George Church's group at Harvard did a DNA capsule that holds drugs, and basically it has logic built into it. So it's made out of DNA. It's called DNA origami. And essentially it's this sphere, and only under certain conditions does it open and release the drug. And so they can build these nanoscale structures that are self-assembled.
Any ideas about semiconductors materials, self-organizing and self-assembly chips and computers in the future?
Yeah, so it's already happening. Probably the best industrial application of pure self-assembly is in semiconductors, in new advances in material science, and sort of the nano to micro scale. And I think it's a great example because we can't manipulate it by hand. You know, if you go from the micro to very macro, we've become good at moving stuff with machines or with our hands and energy, for example. And once you get down to a small enough scale, you can't do that. There aren't machines to manipulate it. And even if they are, they don't have the dexterity that we want. So it's a bit easier to try to guide things into the right place. And so there's this whole field emerging called directed self-assembly, which is about guiding components, guiding particles, all the way down to the smallest, the atomic scale, for example, trying to guide things into behaviors that aren't naturally found, and we can't manipulate them by hand, but if we guide them in just the right way, they will emerge. And there's something called templating. So for example, if you want to create a grid, like let's say the ceiling tiles, you can create a grid, and then you can wash across particles that get stuck to that grid. And then you wash across and they get stuck, wash across, and you can build a perfect lattice without ever having to assemble any structure in there. And they're doing that for semiconductors, and they're doing that for new forms of electronics, that they can have any arbitrary pattern and just wash across, and they'll get stuck in just the right places. And then you can build structures. They're doing the same thing for DNA templating. So the idea is that you can now make any base pair strand of DNA that you want, like AAA, C, TAA, GG. You can make it up, and you can order that, and it'll just be shipped to you. And the way that they do that is they have these seeds, and similarly, they wash across, and it gets stuck, and then they wash across, and it gets stuck, and they kind of do the same thing. So it's not like pure self-assembly because there's still, some guiding, but it can produce these structures that you couldn't have done before. And I think there's a lot of applications at micro to nano. Yeah.
So I know there are more questions out there, but there will be another opportunity for questions at the end. So if we could just thank you, Skylar, now. And
Thanks so much.
So thank you, Skylar. That was really illuminating. Now I am delighted to welcome Calebas Harperis, who directs MIT's CityFARM and leads an anti-disciplinary group of researchers, including engineers, architects, urban planners, economists, and plant scientists. CityFARM is researching the potential for large-scale aeroponic and hydroponic. Here we are not talking about conventional agriculture, right? We're talking about aeroponic and hydroponic food production, aiming to contribute to fundamental agricultural change and develop high-performance urban agricultural systems. Caleb is working on an open-source platform of farming data to improve the evaluation of aeroponics and other farming methods. He was a finalist of this year's Innovation by Design Award. Please join me in welcoming Calebas Harperis.
Okay, let's get set up here. While I'm getting set up, can everybody stand up? You've been sitting for 45 minutes, just like stand up and shake it out a little bit. I know Skylar and I both were taking flights here recently, so both of us are sore. All right, it's a good reset. All right. All right. Now we're all awake again. Hi. Hello. I lead a group in the MIT Media Lab, which is a place of, as Gediminas mentioned, no discipline and kind of intellectual homelessness. And my background is actually as an architect, designing data centers and designing hospitals. Before that, I was a farm kid and grew up in the world of food. And as any good farmer's son, I didn't do what he did, what my father did. And he told me to go out and do something different. So that's what I did, but I kind of have strangely found my way back. So I used to design data centers, which are things that protect computers, right? All the infrastructure around protecting a computer. And hospitals around the infrastructure of protecting people. And now I create environments for protecting plants kind of in the same way. So let's start off with a few easy questions. You know, when you look at this picture, and maybe you've seen this kind of environment before, maybe not, you know, what do you know about the food in it? What's your information? I mean, is this something that you feel safe to eat when you see it? Do you know where it came from? Do you know anything about it? And just answer for yourself. And then step forward into really high-end grocery store, right? We get some labeling, it says some things, but when you hold something that says organic and something that doesn't, and you poke it, you know, does it give you any information? You know, what do you really know about any of this food? Okay, and now you sat down at a restaurant and you've paid $50 for this salad, and you think, man, you know, this is good salad. But now rewind to the first picture. Do you know anything more about this food than you did about the first picture? And the answer could be yes, but this is where you're getting your information. Enter the food information broker. This person, regardless of circumstance, wants to sell you something. So in a grocery store, in the fields, wherever you meet them, they'll tell you what you want to hear, right? And so because they want to tell you something, you can't trust the motivation. Therefore, we have to start getting our own information about our food, which is kind of where the world is now. So the concept is if we do a police lineup, and you get your food on the lineup, you know, you want to ask it some questions and get some answers and create information. So, for example, you know, where did you come from? Which one of you is GMO? How much water did you use? These are the questions that society in general is asking about their food now, maybe that they never have before. But the problem is, you know, food isn't talking to us. And so I got curious. I said, well, how did I lose all of my information about my food when and most of us may be in the audience. So it's been a long journey. It's been about 150,000 years. But 150,000 years ago, we were running around chasing our food. That is our life. That is the way that we survive. Without it, we die, and we need this on a daily basis. So we know where it comes from. We know when things are ripe. We know what things are poisonous. We know what things are beneficial. About 15,000 years ago, we figured out we don't have to run around anymore. We can plant things in one place, and that's the beginning of agriculture, right? And also the beginning, consequently, of civilizations and cities. And then fast forward 150 years, and we get the Industrial Revolution. Now we can be incredibly remote from our food, right? Cars, planes, trains, automobiles. The logistics that are now at our fingertips to create far away from where we live, create the condition of 5 years ago. So it's actually a miracle of modern technology and agriculture that the world gets fed. If you haven't looked into the food system, it's quite amazing that there is no growing going on in any of these major cities, and yet we feed millions of people every day. But maybe that system has reached some limitations. So the easiest way to picture that is, this is the FAO statistics for 2013 of food security. So the countries in green largely can feed themselves, and how they do that is somewhat questionable, but they can. The rest of the world, right? So if you just flip between these two pictures, it's like, okay, so not much of the world can really feed itself consistently. And then it's not quite as easy as this, because compounded in this is the purple countries, right? And the purple countries are being used for food production a lot of time of the green countries. So what's really interesting is natural resources know no political boundaries. So many countries are going around the world buying, leasing land in foreign countries and sending that food back home. If you overlay on top of this what plane, trains, and automobiles have given us, it's a system of food connected by strings, and it's incredibly global. I've purposefully not shown which countries are more of the importer, exporter, and create political mapping. I'm really just trying to show that, you know, I actually just took a flight from the United States to Mumbai this week, and to imagine that food takes that journey is a pretty crazy thing, because I wouldn't want, if I was that food article, I wouldn't eat myself, right? I'm pretty disgusting after I make that trip. And the other thing to know about this kind of a trip and your food. So from the moment of harvest, that live thing is degrading. It's dying, right? Sorry, I know it's sad. But so it's on its way to you, and the longer the distance between it gets to you, and it's been harvested, usually the worse quality of the nutrition that it maintains. So actually, funny enough, if you flash freeze in the field, it's healthier for you than a lot of the fresh food that you eat, depending on how far away it was transported. This system is easy to diagnose. If you just put in the words food crisis, you can see in different contexts for different reasons, whether it's climactic reasons, whether it's water shortage, whether it's pollution. You know, for a myriad of reasons, every country is facing some sort of food crisis right now. And I think it boils down to two basic issues. One is that question about asking for information about your food and getting nothing, which is just, you know, ignorance, and ignorance being fundamentally a lack of knowledge. And so we need to create knowledge and information about food again, so that's one. And the other one is that we have a homogeneous system. And so any homogeneous system is very easily cannot overcome kind of inherent system flaws, right? It has no diversity, has no ability to adapt. And we've created this giant system that's actually kind of a miracle, but it comes with its own problems. So the solution to that is also relatively simple. Although these problems seem so big that none of us in this room can do anything about it, I think that we can. And by creating information and creating a diverse source of interaction with food systems, it's pretty easy to see how we might make change. And let me go through a little exercise on that. So in my life, when I think about the things that have given me the most information and access to the most diversity of information, it's been computers and connectedness. So in the beginning, right, 1960s, 1950s, the computer, the programmer and the user was the same person. That's kind of me right now, right? I'm the maniacal person that understands how to move vacuum tubes and things around in my lab, and it's very hard to translate that knowledge easily to someone else. So what made the computer the thing that today we all, you know, aren't allowed to turn on during lectures? One of the first things, you know, being at MIT and being inspired by people around me, Richard Stallman creates the first general public license, right? This is when software got separated from the hardware. This means that you could work on the software in an independent environment. You could share that with other people. This is the beginning of Linux, the beginning of open source. So now the software is moving on its own and the hardware is more or less static. And then you have folks like Neil Gershenfeld come in 10 to 15 years ago and liberate the hardware in a certain sense. Now, that laid the ground for, let's say, the maker movement now. So now you can work on the software remotely on a computer, you can work on the hardware, you can start doing microfabrication. Those components come out into the world, and we have that culminate in the coder movement, which we saw early on in the 70s, 80s, into the maker movement, which maybe we're seeing in the last 10 years. And then the question for me is what's coming next in that line of reasoning. And I think it will be a fundamentally biologic movement. It will be, how do we create bio-makerspace? How do we get involved with natural systems using the artificial systems that we've created and disseminated? So to create that grower movement, or whatever you want to call it, I think that there are some tools that are still need to be developed. One of those is a tool for creating information in food. We don't have much, so we got to do that. Another is for sharing, and another is providing access to that information, much like a wiki does today. So starting with the creating information and the kind of food fab lab, I began the research thinking, okay, I got to create a whole lot of food in a very tiny place because real estate's expensive in cities and yada, yada, yada. Where's the tiniest place on Earth that they create food? And it turns out it wasn't on Earth, it was on Mir space station. So about 15 years ago, they created a lot of the technologies that I'm working on now, and why they did it was they didn't want to ship water to space. It's very expensive to ship water to space, and so they wanted to use it much more efficiently. And what they created was a system of growing by just using mist. And there's no magic science here. You know, it's water and minerals and oxygen to root systems, which is what they need. But it turns out to make plants grow much faster. You know, rates of 4 to hypothetically 10x faster. So what does this mean? This is soil metrics. This is what we call like a harvest index. So across the bottom is 365 days, 1 year. And across the other side are different things you might like to eat. So if you just focus in on the broccoli. So this means that in 1 year, in 1 square foot, we could produce approximately 3 heads of broccoli. And that's if there's enough water, if there's no pests, if you know what you're doing, if there's not any kind of environmental problems with that. So the NASA data that we start off with would suggest that you could easily achieve a 5x multiple, meaning that now in the same square footage, you know, we're producing 15 heads of broccoli, which is kind of amazing. So then we said, okay, that's not the only advantage of being in a city. So now we've got the, and I did think the math is wrong there, but it's 3 heads versus 15 heads. Take it up just 1 square foot. So if it was possible to do this layering system, which we all see today as vertical agriculture, we've now got 3 versus 54 in the exact same square footage. So then just to be extreme and take 1 square foot of the tallest building in Boston, just 1 all the way up, and we're at a 3 to 3,000 ratio. Now, this is where everyone's a skeptic, myself included, right? And you sit there and you see this picture and you're like, yeah, right, okay, but prove it. So that's exactly what we started doing a couple years ago and building that first square foot. Now, this is where I want to like impress upon everybody that there was also no magic science here. We went to Home Depot, we went to Bed Bath & Beyond, we hacked atomizers, nebulizers, we hacked anything we could get our hands on to try to make plants not die, which is kind of challenging. And I was about to start a little company here on this kind of product scale. And after evaluating this, you know, I realized it's never going to produce enough food to make a difference. And my goal, I was much more interested in producing food that would feed a city than I was producing a couple heads of lettuce a month, which is kind of what you can do with something like this. So then I found this room in the Media Lab that no one knew existed anymore, and I hacked some water lines to it, and I started creating a farm. And inside of this, about 60 square feet full of different LED arrays and vertical growing systems, you know, we were able to produce enough food to feed the Media Lab once a month, which is about 300 people. And you can see from the kind of bright white root systems to the incredibly healthy green color, these plants are very, very healthy, taste very good. You can see this is the first time that most people in the Media Lab had ever torn the roots off of anything. So the question is this a grocery store? Is this a restaurant? What is this pick your own pumpkin or lettuce patch? You know, it's a new way for interacting with our food and still living kind of an urban lifestyle. So that was something that was fun. And then I kept getting these emails, and I get these emails still today, probably at least 40 a day I'm clocking. And the important part to read here would be, I was wondering where you could find data on the optimum growing conditions of crops. Is there a particular database out there that can be searched for various crops, or where the light wavelengths and nutrient thresholds you mentioned were experimentally found? The answer is no. right? This is the information problem. So this is a moringa farmer in Africa asking me for these things that don't exist. And I get these emails constantly, and it's really hard to keep up with. So if you've sent me any of those in the audience, I'm sorry. I was on a plane to Lithuania. But so to answer those emails, we took the work kind of out of the one-off state, and we said, okay, we're going to create a vehicle. This vehicle for the farms is going to be able to travel around the world and be kind of environmentally separate, right? So we create climate inside of this box. So this sits on the facade of the Media Lab right now. It's about the size of a shipping container. And the interesting thing is, like I was saying, inside of this box, we're creating a climate, a completely controlled climate, CO2, O2, temperature, humidity. Turns out, you know, there's genomics and there's phenomena, right, that expresses a gene. So the gene physics, a lot of people are working on gene physics, but very few people working on the phenomena side, or what we might call expression, plant-based expression. So if you can think of a thing that you like to eat right now, and you can think of the best place in the world that comes from, that statement, the best X comes from X, whatever it is. And you know, in some cases, in the States, it's like the best strawberries come from Mexico. It's like, no, the best strawberries don't come from Mexico. The best strawberries come from the best climate that created that strawberry and that expression of flavor. And so inside of here, we create kind of recipes, climate recipes. And so it's like all of the things that go into that plant, and then what expression did it create? So it creates different flavor, right? You know, change the pH of the water and you get an incredibly spicy lettuce. You know, change the CO2 concentration and you'll get a different absorption rate of minerals and nutrients that become available in that plant. All of these things create some difference in that organism. So some people look at this and they're like, this is freaky. I wouldn't want to eat anything out of this. There's nothing natural about it. And to me, what I see is the world is in a box, right? And so outside being natural, well, that's definitely debatable. And so this is just a smaller box within a box of the world, right? Everything in here, you know, you look at it and it's like, why is it purple light? It's purple light because that's the actual part of light that plants use to create new plant material, photosynthetically active radiation. Falls between blue and red, or 400 and 600 nanometers of light. The important part is, one, we're producing that exact spectrum to reduce energy costs. But at the same time, you know, it's kind of purple and awesome. So, I mean, there's two benefits to that. But if you remember from the beginning, the broccoli analogy, and the so but prove it kind of follow-up, this is broccoli that we've created on the facade of the Media Lab in the dead of winter in Boston, from seed in 7 weeks with a perfectly replicable climate strategy behind it. So if you'll get out your smartphone, if you can do that, or else I'll just walk through it. But if you get out your smartphone and you're able to get to the internet, we're gonna dial into the farm for a second. So anybody want to play along? Awesome, we got one. All right, so if you go to cityfarm.media.mit.edu, what I'm working on with the researchers is creating basically like a plant Linux or a plant operating system or a farm operating system and making that open source. We've chosen to do web-based so that everybody can be connected with each other. So hold up some phones when you get to the website and it asks you for a password. Awesome, 1, 2, 3, okay, we have quorum. Username is rethink, password is food, and I'm gonna hope that it's working today. And so the next thing that you'll get to is a very pre-UI, like we're not doing any cute graphics yet. What we're doing is just a functional difference between monitoring the system, so how is the farm doing, and on the other side, browsing the plants, so kind of a plant inventory. If you choose monitor the system, right now, if you just click on that, anybody following along still? Working? Look at that, all right. And then you go into main system. All the sensors inside of CityFARM are correlating to a virtual machine, and that virtual machine is scalable to be replicated around the world. Right now, we have one inside of the Media Lab, so you'll just choose main system. So you'll be inside of the farm at that point. And then let's just pick something on the water sensor board side. So if you pick something like water sensors 3, is it still working? Website working? We got fewer. Okay, yeah, look, you're already at the next one. Okay, next thing that comes up. This is like the gas gauge, the instrument panel of the farm, right? So when I look at this, I look for green. I'm like, oh, okay. And I'll bet you right now, whatever you're seeing, there's some not green, because I'm not there. And my students are there. So if anything looks really tragic right now, shout out and I'll call them. So temperature, pH, dissolved oxygen, oxygen redox, which basically shows you how many things are growing in the water, other things that you don't want, electrical conductivity, salinity, total dissolved solids. These are all the characteristics of that recipe that goes in to create that plant. So the next thing that you can do is if you hit today, the thing on the bottom that says today. And I'm like, how's my farm today? So I'm on the plane here, and I'm wanting to know what's going on, and I scroll in. And what I see is basically all the histories of what the farm's been up to. And this is being collected from seed all the way to harvest. Now, go back to the beginning. The next function is browse plants. So inside of browse plants, you'll see everything that's currently growing in the media lab. Now, every plant, the growth media, has a sensor basically in it, right? And we're able to track, and the system knows when you plant something. So right now, these are all of the things that we're growing. It's the dead of winter in Boston. It's snowing outside just like it is here, and we're in strawberry season, for example. Click on something like the broccoli, because there's a lot of broccoli in the farm today. So when you do that, what you're going to see is all of the individual broccolis of CityFARM have an IP address, right? So these IP addresses both tell me physically where it's located, but also give me a place to correlate sensor data back to. So if you click on one of the broccolis, you'll get this, right, which is a plant profile, which this plant profile says, it's largely, at least right now, still, it works, but we just make stuff up for the data on the top part. But just imagine that you can do things like when you achieve a certain flavor that you desire, you'll set a mark, and that mark will become a downloadable progress bar. And that plant will be downloading until it's ready, and then it'll tell you. The other things is it can give you some information. It can say, my pH is becoming basic, for example, or I'm getting a sunburn, I have too much light, or whatever it is. So you start to create this dialogue back and forth, and there'll only just be more ability to talk with the plants. And then on the bottom is event-based notification. When was I planted? When was I transferred? I'm growing up, all of these things before your eyes. So if you realize that, you just saw the beginning of the plant Facebook, right? So this is now an opportunity, and I mean that in kind of both the funny way, but also, we have a lot of anecdotal information when it comes to our food. Things like, carrots love tomatoes and stuff like that. But what you don't really know is what exact nutrients, what exact ions, what exact salts are each different plant taking out at differential rates. So you can start to do combinatory polycropping, intercropping in new ways to create a lot more diversity in a food system once you have this kind of information. And essentially I'm saying once these plants have friends, right? Friends on the plant Facebook, and then you're able to kind of get in there. So I think there will be a few scales that this will come to us, and it already has started. The personal computer scale, right? This is kind of the first prototype. If you get on any of the crowdsourcing platforms now, you're going to see a ton of this, right? This is where everybody's starting. And I believe everybody's starting here because there's a tiny farmer in the back of our head that says that we want to do this. And then once you do it and you have white flies in your bedroom, you're going to probably realize that maybe you didn't want to do it as much as you thought, but this is a great place for learning. It is a small-scale maker bio space that will go around the world pretty quickly. The next scale, so you saw the pictures of CityFARM before. This is what it looks like today. And basically what I've been trying to refine is some kind of systems architecture so that this system could be modular and everybody else could use it. But I think we're basically in the 1950s, right? This is still the mainframe stage, but this is the thing that's going around the world. But that's the second scale, and I believe that scale will exist and already is starting to exist in restaurants, in corporate cafeterias, in school cafeterias, small-scale local applications. Maybe consider if one's the individual, then one's the community level. And the third level is going to be the data center. So this will be high intensity production in the middle of the city where it has absolutely no food miles and where you're harvesting from this and eating things that are essentially still alive. And, you know, again, you're looking at this thinking, okay, this is kind of like maybe so far out there, it's the Star Trek stuff, it's the food replicator, right? Like is this really happening? How close are we to this? What's the chance that this technology would affect me? This is where the technology is. This is a pharmaceutical manufacturing company. This already exists in a lot in Japan, a lot in Singapore. It's now coming a bit into the United States and a lot being developed by the Dutch plant scientists. So really not maybe quite as far away as it may seem. So then the question is, food systems seem so big. Companies seem to be in charge of everything. Governments and politics seem to be in charge of everything, so what can you do? This is the world that we saw before, and the world that was connected by strings. But those strings are just attached to points, and those points are always cities. So the question is, when we start deploying the personal computer, when we start deploying the server, when we start deploying the farms, how can we do networked production of food for the first time in the world? How can I send a data recipe to Lithuania that then is added onto, that's modified, right? How do we create a community of sharing that's much like what the precursor was for software and the precursor was for hardware? And if this also seems a bit crazy, this is actually what CityFARM's up to right now. So I mentioned that I was just in Anjar, outside of Mumbai. I'm bringing a unit there, and what do they want? They want to grow cotton. And I was like, you know, when they told me that, I was like, no, this is about growing food. You can't do that. And then I had to step back and say, you know, actually it's not about growing food at all. It's about creating information in food, and it's about sharing that across disciplines. And so for Anjar, they want cotton. Why? Because the water table is falling there very quickly. Cotton is an essential part of life, an essential part of all of the jobs in that area. And they want to know in 30 years, when there is much less water, when the environment has changed and they've produced this incredibly versatile or volatile cotton crop, could they do cotton 365 days a year? And what would be kind of the sustainability of that crop? So then go forward to somewhere like Ghana. Our partners in Ghana, when I asked them what did they want, they said, tomatoes cost $14 a kilo in Ghana. We're tired of being beholden to Europe for our tomatoes. And they said, so we don't actually have the climate that could be able to produce a lot of tomatoes. So we need something that can produce a lot of tomatoes in a completely independent climate. So that was kind of their motivation. And the point is, every place in the world, every person in this room would have a use for this technology that would be different, right? And so when people are asking me, and what I'm creating a solution, and to what problem am I trying to solve, I think that it's sort of like asking in the 1960s, what's the point of the computer, right? And there were probably answers then that were quite wrong, as it would come to today. So I think everyone in the room being so emotionally involved in food will want to do their own thing. Therefore, we need platforms of sharing. So this is kind of what I imagine and what our work is going towards. So it's the Fab Lab model, which I've explained, the Linux, everything being open, and the wiki is the plant recipes. And it's just a platform for connecting, you know, a manufacturer with a biologist in a real-time, you know, new form of exploration. It's about connecting nutritionists with activists. It's a product that makes us all conversant in food and able to contribute from our own discipline. So I'll end with this and leave us some time for questions. If you've ever wished that you could go back, travel back in time to the beginning of the internet, right? And you're like, I would have invented Google, and I would be super rich, and I would not be in this room right now. If you've ever felt that feeling, I really believe that the internet of food or the internet of edible things, you know, is now, and it's being planted now, it's being sown, and there's still a lot of ways to become involved, and I hope you choose to become a farmer. So that's it.
and then we'll come back again.
Oh, because there's a question right at the back.
Go
Right at the back, on this side. I can show. Sorry, there's a lot of running involved.
Hi, thanks for the presentation. I was wondering, what is your view on food is also connected to open source and coding that doesn't involve food itself, which is Soylent and similar products?
Okay, great question. I just threw this conference in Napa with the Culinary Institute, and we had a panel called Fake Food. So if you're interested in hearing from Soylent directly, or from Beyond Meat, Meatless Meat, or Hampton Creek, Eggless Egg, all of these things, you can hear directly from the founders on that website with Rethink Food. But I could also take this into a question of science and technology and food, and why that's scary, and why in this room, there's probably a majority of people that when I say the word GMO, get like this repulsive feeling inside of you. And then there is the portion of the population that doesn't. And then there's the portion of the population of farmers that said without that, the world would starve to death and half of us wouldn't be in this room. So then the question is, why is there so much emotion and very little knowledge? And I believe that knowledge has been siloed. And that's a product of a system. I don't actually think that anybody in the system is inherently evil, although other people do. So the question about fake food. I think that, we don't exactly know if Soylent, for example, which if you don't know Soylent, essentially the developer of Soylent would just like not to eat food. Like that's his position. He says, I don't really like eating food. It's a pain in the butt. I have to go to the store. I have to buy stuff. Then it spoils. I have to learn how to make it. I don't want to. I want to drink water, and I want that to be healthy and give me all of the things that I need. That's a response to lifestyle, a desired lifestyle, and meatless meat, for example. Meatless meat is coming for a number of reasons. Meatless meat is coming because we're in a protein dearth in the world, and we're only going to continue to be. And if you don't, realize that and how much we're going towards a plant-based diet, you should check it out because we're all going to be eating plants and many less animals. So I think that's a response to both an ethical and resource limitation that we're going towards. So I think each one of these are expressions. And that's really just expressions of people wanting to be engaged in their food again, right? I think in the 70s and the 80s and the 90s, we just wanted a hell of a lot more food to feed the world, and we didn't care, and we wanted it to be cheap. And very few people were invested in that emotionally, and we got it. We got the system that works to create a whole lot of cheap food. These fake food, or I even say the fake food is on the same continuum as the organic gardener. The organic gardener that's coming up. They're really not so different. The organic gardener wants to know where their food came from, wants to know what's in it, wants to take part in it again. And it basically come back to a place of trust. Soylent, maybe they don't trust food at all. Organic gardener, maybe they don't trust any industrialized food, but it's a reinvestment culturally in our food systems, and I think that's the point of time that we're in. The consumer's asking for something different. The science is able to play a part of translation in that in different ways, whether that's the extreme, non-GMO movement or that's the extreme synthetic biology movement that's going on in food. Hopefully that wasn't too rambly. Is there another question? No? Yep. Course. So one of the number one questions, and I'll be the first to say that we don't know yet fully that answer. But we are creating metrics that don't exist in current conventional systems. Let me describe the conventional system, and then I can describe how we're approaching that problem. Conventional system is a series of arm's length relationships, right? So you have the grower. The grower is not reporting energy, right? They use all different kinds of energy, but they don't really care. They're creating a product. Then you have the distributor. The distributor is taking it to a packing facility. It's either a co-pack or it's a cold storage. Then it's going on, again, to its point of eventual consumption, and that could be retail and whatever. There is no reporting of data along that string in a coherent manner. And even if there was, below that system is a system of cross-subsidies. Depending on which government that you happen to live in the country of, they're supporting food in a number of ways. You know, in the United States government, for example, they actually pay farmers not to farm as part of the subsidy to leave land fallow. I mean, it's a very, very complex thing. This is a project that we're taking on with a group of economists at MIT, but you know, we're getting there. What can we do about it? What I do in the lab is I've created a few units. One of those units is kilowatt hours per grams of fresh weight. So a very simple, very non-negotiable, very apolitical thing. And it's to say, every time that I grow something, I have all the information from seed. I take it out, I weigh it, anything that's edible anyway, the edible plant mass, and I say, okay, it took me this many kilowatt hours. At MIT, I pay 9 cents a kilowatt hour, and I can produce this much food. And to give you a concrete example of how much that costs, all in energy. So all of the devices inside of CityFARM at the beginning tweeted their own energy use just for fun, and now it's much more like a server, like a data center, right? Every plug has a reportable unit that's coming in for consumption as well as control. So right now, a head of lettuce, you know, which is a pretty easy thing to grow, and which is why you see a lot of these people starting with lettuce. A head of lettuce in CityFARM, all energy in, is costing about 60 cents at 9 cents a kilowatt hour. That does not include labor. Does not include amortized equipment, does not include rent, does not include a lot of things. But we're kind of at the beginning. So that's one metric, kilowatt hours per grams of fresh weight. The other one is liters per grams of fresh weight that we're reporting. You know, water is also a huge problem and also a huge cost. So developing these metrics over time, getting that platform out to as many people as possible to verify the energy use, to then even locate where the biggest pinch points are. You know, when you look at the lab, you think it's got to be the LEDs. Actually, the number one consumer of energy in our environments is the HVAC system. Light, everyone thinks, why don't you use light? It's free, right? Why don't you use the sun? It's free. 10% of light that's produced by the sun is utilized by plants to grow new plant material. That means that the other 90% is not. That other 90% contains a lot of heat. So if I was to open up and take on as much sunlight as possible, I would be the greenhouse problem, right? I would be taking on so much heat that I have to open up the system, therefore I lose control. That's where all these greenhouses have big problems with pest infestations, and they have big problems with disease, bacteria spreading. So I don't know if that answered enough of your question, but it is to say that getting more of these things out there, getting people that are have the concern and can pinpoint these problems. If the problem turns out just to be HVAC, we can solve that. Right? If the problem is more on the LED side, we can solve that. Actually, on the LEDs, I mean, you'll know that this year the Nobel Prize was for the blue LED. The blue LED is absolutely critical for everything that I do. Controls a lot of the morphologies of the plants. So I think we're on an optimization curve for food. We've just yet to create a cohesive system to act within it. And then I'll say one more thing. When you see the pharmaceutical industry or you see a few of these vertical farm projects going on, just think of it as like a pre-Fordist moment, because each of these people and organizations around the world are creating these one-off cars. And it's easy to point at one-off cars in the beginning and say, that car takes too much gas, it'll never work. Cars will never work. That car doesn't go fast enough, cars will never work. Nobody will want to go that slow. Blah, 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 along the line. It's only because we're in a moment when food hasn't been thought of as in this kind of agriculture hasn't been thought of as a system. You know, and that system can be optimized by a series of components. So that's really the architecture and the groundwork that we're laying right now.
Okay, so if you could just keep incubating those questions for a moment while I invite Skylar and Calebas to join us. But then we can,
Yeah, this is one.
yeah, okay.
But just curious about diseases and vaccines.
Oh, awesome. Okay, this is fun. So let me start by saying When you see that farm and you think it's weird and crazy and emotionless, and you think, you know, there's the soul of farming is gone, and the soul of the food is gone. Google CityFARM, then look on YouTube, and then put Marvin Gaye. What you'll find is a video of us pollinating our flowers. It's an incredibly intimate process. We take a vibrating toothbrush, and we self-pollinate all of our flowers. And it's very, you know, like there's an investment that's made in this reproduction. But then to the more serious point, in these environments, I use no pesticides, I use no chemicals. How do I achieve that? I achieve that because I can use things like integrated pest management strategy, which just means other bugs, right? Beneficial bugs. So inside of the Media Lab, probably on a monthly or bi-monthly basis, I go to Amazon and I order 1,500 ladybugs, and they come Amazon Prime in one day. Believe that? It's true. And I release the ladybugs. The ladybugs take care of a lot of my pest problems. I also release things like green lacewing. I also release pollinators. There's a lot more of a permaculture application that can be investigated here, but related to the bugs, that's what happens. And then on the disease side, you know, imagine that inside of here, these plants are in plant, you know, pick your religion. I mean, I could say heaven, or I could say nirvana, or whatever. These plants are incredibly happy, so they're in continuous growth stage. And because they're in that continuous growth stage, they're incredibly resistant to disease. Now, I do have waterborne disease, and I can combat that with beneficial bacteria, for example. So we're kind of living in the Wild West of this field, which is there is 10,000 years of knowledge in food systems and in agriculture, but there's very little knowledge in these new systems. So I would also say that on that topic, one of the hottest research areas that actually MIT just now announced a school of is the School of Researching the Microbiome. So the question is, and I don't know the answer, is this food grown this way as healthful as food grown in the ground? I would answer that question very easily by context. If this food is grown right outside of a city, of a major industrial area, it's probably healthier coming from my lab. The carcinogens, the water contamination, the soil contamination. But is the beneficial bacteria there? This is a question that nobody knows. This is a serious point of my research. Some of the food that you saw inside of CityFARM we eat. We plant the things that we like to eat because it makes it fun. But then part of it is for later analysis. So we are doing analysis of the food crops down to the sequencing level to see what gene expressions we've created and how that differs from greenhouse and from in-field. But again, still at the beginning of that.
We're not stopping questions, we're just reconfiguring. So Skylar, would you like to go into and get
We can do.
Can you hear me? I just wanted to ask both of you. Skylar, you mentioned talking about your research to different research groups, and they had different ideas in terms of applications and response. And I wondered whether the two of you could see connections between the two pieces of research that you've just presented, between your research.
Yeah, I think at some point when I was speaking, I started talking about food and cooking and gardening, for example. And I think there's a lot of interesting scenarios there that relate. And one thing I was thinking about as Caleb was presenting was this question of efficiency, whether that's manufacturing efficiency or whether that's gardening efficiency or any other efficiency of production, especially when you're dealing with a complex system. And I think whether that's cooking, gardening, manufacturing, cities, all these things are super complex. Many, many inputs, many outputs, and complex systems by nature can't be predetermined and are very hard to engineer, but we live in a complex world. And so, there are interesting ways that we can, have a dialogue with that in a productive manner. Not just saying, well, shit, we can't do anything, it's out of control, or saying we can control it, which is what we've done with urban planning, for example, which is totally not true, that you can control complex systems. So there has to be this like really nice dance in the middle, and I think it's super inspiring what Caleb's doing, and really trying to be rigorous about understanding it. Everything you do is going to have other unintended consequences, but you're trying to allow the thing you're working with to communicate to you. And in some ways, if you listen carefully enough, those systems tell you what they want, because they want to be comfortable. And so they're trying, essentially all of these systems, whether they're plastic particles or balloons in the air or roots or all, are trying to find comfortable scenarios, and they can give you hints as to how to do that, and therefore they'll be more productive. And so I think that's a really interesting one, especially for the manufacturing side. And the manufacturing side, I think, is way far behind compared to what Caleb is showing, especially thinking in that vein, because we've traditionally thought, okay, if I want to be more efficient, I'll just put more robot arms on my assembly line, or I'll put more people. That's a very linear relationship, which is like, there's no flexibility, and you can never separate that. And so if you can work with complex systems, you can have huge efficiency increases, but then you have to be okay with losing a little bit of control. Anyway.
Yeah, I mean, I really, it says, I really couldn't agree more in a way. It would look like, in one way, that I would be in control of these plants. What I am is driving a car that I'm not even driving the car. I'm sitting in a car, and I'm trying to press the gas sometimes and the brake sometimes, and the car drives itself. Related to Skylar's work, there is a big push right now in science for let's say, the biologic to meet the mechatronic, and to understand what is the interface of the biologic and mechatronic, and understanding it from the building block scale, which is probably the most, I mean, it's maybe even more important than the complex organism scale, right? Because you're looking at the tiny thing that makes all of the changes later. And then coming back at it from looking at what those changes made and then saying, how could I have shaped this differently? Let me give a concrete example. So I have a project starting about winemaking. And the question the winemaker had was, during a year, I can't really control the vineyard. And things happen. We get a drought, we get too much sun, we get this, we get that. It completely changes the flavor of the wine. Now, they can make local corrections. And those local corrections, I think, is a lot about Skylar's work that was presented. How can we program in some intelligence that we don't actually know the end solution? So that, for the winemaker, would be the local correction, where they can go in, create a temperature difference, put a humidifier, put a fan, put a something. And that will eventually influence the way that grape tasted later. Now, where I come in is they said, well, what if I would have done something different? And so we're actually starting a project where we're sensing climate in Napa Valley. We're trying to recreate that climate inside of the lab and essentially set up like a parallel universe where we'll make a different decision than the winemaker made, and then we'll create a wine and we'll see what happened. So I think, again, the parallel between the physics of genes and the expressions of genes is also somewhat of the parallel of what we're talking about. Understanding first the physics and the mechanics of the system to then be able to create expressions with that system that maybe we aren't actually in control of.
Yeah, and I think in our case, the gene is the geometry, the interaction, the components, how they move around, et cetera, and their environment. But you can't isolate any one of them. If you only focus on the geometry and the interaction and like the gene, for example, everything else in the system is going to screw with that to do what it wants. If you only focus on the environment, you don't care about the gene, then you're not going to get the same results. So you kind of have to like play this dance with all of them and understand that both have, or let's say all three in our case, the environment, the behavior that you want to produce, and the components all have super critical roles in that dynamic system.
Actually, I wanted to ask you the question about empathy. Because Caleb, you were talking earlier in your private interview about the empathy, like that plants may have empathy. And of course, as we're getting more and more understanding, of when we speak about other beings, non-human beings, right? That other beings, they do also have soul. They also have consciousness, right? So what is happening actually with the plants in that sense, and also with the water? Is important for you? Do you developing that type of thinking to master instruments that could actually read that type of data?
So if we go back to the beginning of the presentation where I put the 2 tomatoes up and I tried to ask them questions and nothing happened, I sadly feel that every day. And then I think about what information did I just show you? The information that I just showed you was really just the environment. So how do I get information from the organism, right? How do I speak their language? And the language of plants is a visual language. Everything that I do creates a physical reaction in that plant. Take, for example, something as simple as too much nitrogen. Too much nitrogen applied to the plant will create a yellowing burn. You've probably seen this in your houseplants, or too little sun, for example. Each of these variables produces an immediate physical response. So I have to tell you that if you've ever had a plant in your house and then you were really attached to it and then it died, I'm sure you felt something, right? You may not have felt sadness, you may have felt frustration, you may have felt a lot of things. But plants have that ability to evoke emotion from us because we know that that thing was alive and we couldn't help it and we tried and we wanted to. The other interesting thing is, take for example, if you put light too far away from a plant, the plant won't necessarily die, right? The plant will stretch and stretch and stretch, elongate itself, adapt to that low light condition. And I think that those physical, whether it's a morphological trait, whether it's a chemical trait, for example, really what you're doing with taste of plants is you're creating stress. So to give a small anecdote on that, we had a harvest, we took the lettuce out, we fed a bunch of people, and we had some left. And because I feel morally and ethically invested in this lettuce, I can't throw it away because I watched it grow. So I put it back in the lab. The next day, we tasted the lettuce, it was incredibly sweet. And I was like, oh, somebody at the media lab spiked the water with sugar. Like, let's do some analysis and figure out what's going on. So we did tissue analysis. What actually happened is that plant, I realized we fell backwards into plant physiology, and that plant had an induced drought state. That drought state created an emergency for that plant. That plant was trying to protect itself. So that protection transfers into a chemical change in the plant. That chemical change, from it trying to survive, tastes different to us. So it's all of these signals that they can give us that tell you how invested they are in the care that you're giving them. And I think when you're around the plants, it's easy to throw shit away when you bought it from the store and you didn't watch it and you weren't invested in it. But I can tell you now that just having that lab in the media lab, I get texts and emails all the time, from people I don't know that are like, what's up with your tomatoes? Your tomatoes are looking sad. What's going on? You have this plant and it's dying. I've been watching that plant grow. Why are you killing that plant? All these people that I don't know are invested just because they're close enough to us, which is, I think, really what people miss about being with the plants. And so I think the empathy, at least up to this point, has been created on the side of, on my side, for the conditions that I'm putting, the plants in. And I think they'll be able to speak back to me as I learn to speak their visual language. And then in that way, start to communicate.
You're a tomato whisperer.
Yeah, I try.
Should we take yeah?
Great question. So again, we'll go back to the GMO scariness, which is probably the genesis of that question. So for a long time, we've been putting technology in seed. We've been embedding technology in seed now. And that's for an adverse world. And we call that biotechnology, or we call that genetically modified, or whatever you want to call it. We did that for a reason that we couldn't really control the world, right? And you made a seed more drought tolerant. You made a seed more pest resistant. You made a seed do all of these things that it couldn't do by its own. So then the other end of that spectrum is perfect world, which is maybe what you saw on Mir, right? And what you're seeing now on Mars 1, which is unscalable, completely unscalable. But in that kind of world, there is no biotechnology that would be relevant in that world. So for my research, I use rare seed, heirloom seed, hybrid seed, and that jives with everybody. They're like, oh, good. But I really do it because there's no advantage to me for biotechnology, right? That all of the biotechnology that's been invented is for the adverse world, ergo I don't have one, so I don't need it. One cool thing is I work with rare seed banks, and I can put back into production varieties that haven't been in commercially available in 50 years or 100 years because of crop selection. You know, like we chose crops that kind of fit our lifestyle and our practices over time and got rid of the ones that didn't. In a system like this, any seed can do what it does best, which the seed is already programmed to grow. So that's, kind of the seed issue as it relates to the farm.
I have a question about Caleb's idea. It's obviously wonderful and much needed in this wave of this crisis that we are facing. But on the other hand, in the long run, don't you feel that by providing humans with this almost limitless resource, we might create a bigger problem of overpopulation?
Right. The flip side of that is don't do it and let a bunch of people die. So that's it would depend on your ethics to answer. But I would say that more of what I'm interested in is creating inventors related to food. Less of what I'm interested in is producing food. Does that make sense? Like, we don't have that many people from various disciplines working on food problems effectively. Over time, we've become hyper-specialized, incredibly vertical in all of these fields, and really now is a time for a horizontal understanding of food again. So the technology I'm working on, yes, there may be solutions. Yes, most people see it and assume it's a machine for spitting out food. But really, the reason that it's open source, the reason that I'm trying to speak the language of kind of contemporary inventors is to bring more people and more thought and minds into it. Will we reach a point? Here's another answer. Would it ever totally replace conventional agriculture? A lot of people in my field are like revolutionaries, and they're like, there's disruptive technology going to great. No, this technology represents less than 0.5% of global agricultural production in the world right now. Let's just be real. So getting this up to 5-10% would be a monumental feat, and it will be over the next 5-10 years. I think in that time, as we create people that invent with this system, we will create solutions, to your problem, to that hypothetical problem. But in the same way, this technology is being used in Mars for Mars colonization. So if we had too many people, we might ship them somewhere else where we're creating food. I mean, it's reasonable.
So I have a question for you actually on that note was about forest fires. Like there's a lot of interest or let's say discussion about how complex systems often have to purge themselves. Mm-hmm. And a forest fire is a good example that, as we've created forestry services and foresting as an industry, we've tried to stop forest fires from happening, but that's often one of the most useful ways to create healthy forests. And so how do we, in agriculture, how could we deal with that in the future?
I don't know.
Like, are we going to burn down the CityFARM every 5 years and then start again?
Well, here's a kind of an answer. What's my bottleneck? Like, what am I worried about right now? I'm not worried about the technology. It's largely there. Like, not much of what I'm doing is, I would say, novel. It's more systems integration than anything else. My pinch point is minerals, believe it or not. So, like, I need things like nitrogen, phosphorus, potassium, calcium, magnesium, boron, macro and micronutrients. some of these things are from finite sources, at least at this point. You know, we kind of got liberated with the nitrogen because we can make synthetic nitrogen, you know, out of air and all of that, but something like phosphorus. So I don't know exactly how we would purge systems, but I see how the systems will purge other systems. And what I mean is, I get contacted quite a lot by big companies that say, I have this byproduct, and I used to throw it in the ocean. And when I threw it in the ocean, it grew stuff. And then the EPA didn't like that. And now they charge me a hell of a lot of money to get rid of my byproduct. One of those byproducts is chicken waste, right? Another one is yogurt factories have a byproduct that's high in phosphorus and high in potassium and calcium. So they're like, I pay to get rid of this thing. So then I'm starting to think, oh, okay, so you're going to pay me to take the thing that I need. That sounds awesome. But what I think is going to be a major advancement on the purging side will be more of understanding. See, I think that there is a bigger use for CityFARM maybe that's a little bit far out there, but one of those is being involved with city waste streams. Pretty much everything you need to grow is passing through you very often, several times a day. We do some pretty terrible things with that waste as a urban society. So I think part of the purge could be related to becoming a cleansing device. Does that make sense? Like I don't know. And then the other one is CityFARM attached to your toilet. How many would eat that, right? But the other one that is also very interesting is my environment. I keep at an ambient CO2 of about 1,000 ppm. That means nothing to most people in this room. Ambient CO2 level is about 500 ppm. This is something that everybody's worried about, CO2. I need it. I need a lot of it. The plants don't survive without it. If you had no CO2 in the environment, they would consume it all and they would die. So I actually need something that the whole city produces and is causing us problems, both health problems and environmental problems. So maybe the biggest value of CityFARM, instead of planting a forest and getting a carbon credit in, you know, Minnesota, like maybe a CityFARM becomes a value-added point source carbon credit that can be extracted out of a city. Now the question is, are you sequestering the carbon or not when you eat it? I think that's another question. But it's just an example of how a macro system can be affected in maybe a new way with this technology.
And I just actually also wanted to add one aspect in terms of the kind of like number of the population, you know, that may kind of like grow just thanks to your you know, wonderful invention. But in fact, it is another aspect that, you know, that was maybe not mentioned tonight, is that we have the responsibility for what we eat, you know, not only in terms of our own bodies or our own environment, but also in terms of the coming future. According to the, I think, health organization, you know, data, our body carries about 272 or 75 toxins, right? I may be wrong with the number, but thinking about that, you know, that for what we eat, we accumulate the toxins and we leave them on this planet for the future generations, you know. We could also think about, you know, the food systems in that respect, you know.
Yeah, definitely.
Have you thought about cooperation between your researchers? I mean, like creating some kind of adaptable structure for growing plants, or does it have any potential?
Haven't thought about it.
We just did right now.
Nice idea. I guess you're proposing sort of like the 4D idea that you have some physical structure that transforms, let's say, light levels, or infrastructure, let's say, I don't know, fluids that you can move around or things like that. You can control adaptive piping and things like that. I think it's a good example of where like infrastructure systems, whether they're for a farm or for other cities or et cetera, we've designed them in traditionally super rigid, static, over-engineered ways. And in the beginning of this work, before we even did the 4D printing, we were looking at water pipes. There was a company that came to us to try to look and produce adaptive piping because basically the problem is that if you have, pipes are designed for peak demand, whether that's like user demand or surges from storms and things like that. So you have this massive pipe that is almost never used at that capacity, and then sometimes it bursts or it gets old and you have all these complex valves and stuff. So the idea would be a much more lean and adaptive infrastructure system that could move water, that could expand if it needs to expand, contract when it needs to contract, become the valve itself. So I think in that sense there's maybe some thought there about how we could approach some of those infrastructure systems, but lighting is another interesting one, yeah. I think it relates to all of the complex systems that you're pointing to, whether those are economic models and financial models or population or startup world and that space. For sure there's going to be bubbles, and I think one of the situations with dealing with complex systems is that they're unpredictable. And you can have lots and lots of models to predict them, but one of the fundamental properties of a complex system is that you have to play it out to see what happens. And so in that sense, I think it goes back to the forest fire discussion, which is that things will happen. Things are never going to not happen. And the question is, like, how do you work with those and how do you adapt? And so I think one interesting way is to build in adaptive systems into that environment. So as things are going, you can be learning about what is happening, what is about to happen, what change just happened that is out of the ordinary, and then adapt on the fly. And so in that sense, it's not like we've established an environment, a manufacturing setting or a farm or whatever it is, and when shit hits the fan, and we're like, oh crap, but rather it can fluctuate and try to mediate some of those. But I think part of it is that you have to understand that there can be great benefits, and there are obviously drawbacks, and the biggest drawback is control, as compared to, especially in manufacturing. Control is the biggest one. No one wants to lose control in a manufacturing setting, even if you could say you have huge efficiency increase, or that you have products you could have never made before, or you can have 24-hour cycles that don't need humans or machines or all that, because they're worried about those super marginal moments. And it's not that we shouldn't be worried, but I think you have to have an understanding that things happen, especially in complex systems. Yeah.
So, a lot of questions about doomsday today. What happens when? But I can speak directly to what math, we're working on, and what the value of mathematics is in the work on farming, which is huge, related to the amount of information that we're generating. So most of our math modeling, or our algorithm development, has been around the fact that we don't actually know, even just these 20 variables that I'm collecting, let's say, the atmospheric and the waterborne, we don't actually know. We know those variables as blunt instruments. We know, like, too high of temperature, the plant's going to die, right? We don't actually know the correlative data between CO2 saturation level, temperature level, and dissolved oxygen level, and what that creates in a plant, right? So I think that's where the algorithm development becomes really important, is to deal with and understand and make useful the just absolute immense amount of data I mean, you could see CityFARM as just a data factory for one thing, like because we're producing so much differential information. So I think the mathematics mostly we've been using for that. In terms of modeling environments, I've honestly stayed a bit away from creating mathematic models of the way that the environment is working, and I'll tell you why at this point. At this point, it's because you might create a mathematical model for weather, and it might tell you a general tolerance, but I don't really care about general tolerance. I care about when the cloud is in front of the sun, and when I should raise my PAR levels on the lights, and of what spectral quality and intensity that light has now shifted to. So therefore, creating the models for me would be a little bit less useful. So I've focused on real-time structure for evaluating information, such as when a cloud goes behind the sun, I have a sensor that's telling me what the new spectral composition and intensity is. I don't know, does that answer a little bit of your question? And I think in terms of world ending, you know, two things. One, 2012 invention of the year, Time Magazine invention of the year, verticrop. Biggest vertical growing system, supposed to be amazing, tons of money. It didn't have the problem of having enough money. It had the problem that that no one had studied the economics enough, that they created a one-off thing and scaled it. And when they scaled it, that percentage became incredibly small between making money and losing money. And they lost a lot of money. And they couldn't go back and adapt their system to Skylar's point. It was a one-off design that they couldn't then identify the source problem and then eliminate the problem in a very rigorous way. So I think that's one of the biggest risks right now related in my field to the analysis of energy, is just that all the systems are different, and therefore making some mathematical correction is a pretty hard task. Oh, I lost my thought on the other one, so that's it. That's all you get.
I want to pick up something on the modeling side. In terms of modeling and simulation, I think there's two camps, at least in materials modeling, for example, and not to mention the tanks. And one camp is that you model as accurately all material properties as you possibly can, and just model till you're blue in the face. And mostly we've gone the other camp. And the other camp, my mentality is that what we should do is simulate and model to get the fastest results that achieve the best that we need in the given amount of time. So therefore, minimize the accuracy at any local point of your model, but build a lot and try to correlate the two. So meaning, like, if we can learn a lot, if we can simulate a material's property, why not just build the material in no time at all, analyze what it did, and then feed that into our model, instead of trying to predict everything it's going to do the other way. So we try to have these kind of abstract simulations that will give us geometric information, they'll give us file outputs, and then we can try to link those with what's physically happening. And everything we do is not a success in my mentality unless we build it. Mm-hmm. So we care much less about how accurate any one of our models or simulations are, but rather that we would like them to talk to each other so that they could give input to one another. Like the physical can be inputting to the digital, and digital can then be feeding back to the physical. And I think then they'd be communicating and building a stronger model collectively. But it doesn't do us any good if we can simulate this awesome thing if we can't demonstrate it in the physical. And it'll take way too long to simulate a lot of the things that we're doing.
And maybe one last point on it, from my perspective, I basically am trying to create a socket to you as a mathematician to give you valuable data to be analyzed. Right now, everything's in the theoretical related to the work that I'm doing. They put in the variables they think are there, blah, blah, blah. They put out some output, and then they lie, and they say it either works or it doesn't work, right? And that's just totally made up. So in creating these data points for you, I am hoping to build the bridge into more advanced mathematical analysis that's based on conditions from the built, from the constructed, from the grown plant. So.
Yeah, it's a hairy subject. So I've gone all over the spectrum. At some point I've been like totally open, other points have been totally closed, and now I think it's a really nuanced discussion. And I think I think it's dangerous to have these perspectives that are like everything should be open or everything should be closed, but rather there's like very delicate instances in all of them. And I'll give you a strange example, which is that MIT as an institution is open. It's an educational space and supposed to be open, but almost all of their research funding is from industry, and they're fundamentally closed. And so you get in these random situations where the company's like, no, everything needs to be closed. We want to patent the hell out of this thing, and we're going to not tell any of our competitors about it. And MIT's like, look, we don't do that. We're an educational institution, and everything needs to be open. Yet somehow they've resolved this issue and have been for however many years. And so basically it comes on us, and we have to deal with that every day. So I think there's a lot of ways to deal with that and try to have an open mentality, but maybe it's not about giving every little piece of the information, but trying to open up let's say open up the process so that other people can engage in it. Having a larger discussion about it, maybe not talking about one application, but saying, look, here's how we did it. Here's the key ingredients to doing that. Let's work together, or you guys can do it, but maybe you do it in a different space, or try to figure it out based on what we did. Other ones you can be completely open. Other ones, there's a mandate to be closed. And I think it kind of goes in and out, and it depends on the application, depends on the scale, depends on if it's for-profit, non-profit, if it's government-funded, education, focused, there's all these different nuances.
Okay. I'm like in the middle of that world with lawyers around me. And here's an interesting thing. If you want to be open source, that does not mean that you don't protect your intellectual property. Seems weird, right? Why would I protect intellectual property if I'm going to be open source? Well, I learned that one. And that's because I started sharing things. And there are these trolls that come around, and the trolls watch you. And when you share things, they try to patent them against you. And if they patent them against you, then they take that away from you, and you can no longer share your thing, whatever it was. So please don't take open source to mean that we're all back in the 70s and everything's happy. Like that is not open source at all. Open source means strategic use of intellectual property for a certain goal. So I think to Skylar's point, it depends on the stage that the field is in, as much as it depends on what your goal is and how you're going to achieve that. In my circumstance, I'm trying to create an ecosystem that doesn't yet exist. So therefore, the people that I think are patenting technology in my field right now, that it is relatively useless because it's not attached to a scalable system. And so the likelihood of people paying for their intellectual property to be used in application is very low because it's very specialized and really just not attached to a bigger system. So I would advise that if you're doing anything that I'm doing related to that, and you're starting to spend money on intellectual property, that you just stop. Because it's relatively unprotected. I mean, it's hard to enforce. If you go across global boundaries, it's impossible to enforce. I could have gone that way, but I didn't. So on the open source side, what I've had to do is I've had to make all my IP disclosures, all my patent filings, all of that stuff with the commitment that as it is protected, it will be royalty-free use to any user that abides by rules. And I set those rules. And those rules will be, this remains open. So there are different ways to enforce that. One is through a trademark. Sorry if I'm getting technical, but it's interesting because I am dealing with it. It's keeping me up. Trademarking. So if they want to be in the CityFARM network, for example, they have to abide by the rules. And those rules are all data, all hardware, all software remains open. I can enforce those rules by if they're using the technology, I can come back and say that technology is actually licensed to you based on these rules, therefore you violated the rules, therefore I will prosecute you. So open source is not without teeth, and it is not to be done lightly, or someone will just protect you and then out of it. But for me, like I said, it's to my benefit that all of you guys in this room get on this network, because I just want to see what happens. Like, I just want to see that. And so for me, I've got to get to scale fast in what I'm working on, or there's really very little value. So like, that's why I chose to go open source. And plus, I just like showing people what I'm doing.
I was at a conference last week called Biofabricate, and it's very similar to what we're talking about today. It was talking about the maker revolution with biology. And so there's a number of companies out there like Modern Meadow and Organovo and Ginkgo Bioworks and all these people who are using SynBio to grow and make stuff, right? And then there's like the makers and hackers, and there's the researchers, and interesting space. But the startup people had a panel talking about IP, and one thing that really resonated is there was a number of young entrepreneurs, and they were saying that really like the IP system is this shitty thing that we inherited from the previous generations, but we have to play the game. So they found ways to play the game, even though no one believes in it. The people in the system don't believe in it. You go to get a patent, and we've done this multiple times, the lawyer has no idea what you're talking about. They write up all these claims. You have no idea what those mean. You can't defend it anyway. People can steal it from you even if you tried to defend it. It's all this like bullshit. But everyone just plays this game to play the game. And so those guys, their mentality was like, look, we're going to patent stuff. We don't really care about it. We're not going after anyone. But we do that because we need to be in the game. And we need to have a conversation with other people. Otherwise, they wouldn't take us seriously, and we can't move forward. And so it's like this weird system that we have to play, but everyone's just playing it.
Ask you, you are solving very important problem to avoid stress, and this creates healthy plants. But from another point of view, it's need increased yield of the plants. Do you using some grow promoter or immunostimulator or some treatment of seeds before start to grow? And second, my question, how regarding storage? You some during storage with products, you create special conditions, or just go to realization?
Like storage post-harvest,
Yeah,
you mean?
post-harvesting.
Ah, okay.
And first, for me, what you using
Yep.
promoter or
Fertilizer.
modulators to see yield, fast growing
Right.
conditions.
Right. Great. So, am I using like artificial hormones or something? No. I'm sorry to give maybe too cursory an answer, but it's very, very simple. I'm using base minerals. I'm using the minerals that sometimes may or may not be found in soil. When you think about soil, soil is structural substrate. And sometimes that structural substrate has good things in it, and sometimes it has bad. I don't need a lot of the chemicals that you may need to be achieving a commercial yield in this kind of environment. I'm literally, and I can show you the pictures, and if you're interested, I mean, I can give you the recipes, because I intend to do that anyway. But I am literally using NPK, right? The biggest macronutrients for plants, nitrogen, phosphorus, potassium. And then all of the micro. And those, now the question is, where do I get those? And that's a bigger question of the mineral game of the world, which we could get into, but maybe it falls under another conversation. So no, I am not using any artificial hormones. I am not using any chemical growth inhibitor. And am I getting commercial yield? Well, it depends on how you look at it. Commercial yield in the field, there's a lot of loss by the time it comes to market. So then what is commercial yield would be a good question. So by time it gets to point of sale, you know, how much loss has been in the system versus how much can I create at point of sale. And the second thing is, I showed you or I was talking about the concept of flash frozen versus fresh eating, and why that's crazy that flash frozen would be more healthy for you in lots of cases than fresh eating. If you're curious about that, Davis wrote a paper on it, UC Davis. Check it out, it's for real. Flash eating would be more healthy than flash frozen. So in terms of storage, I don't store things very long. And the concept is not to store things very long. The concept is from like 30, it's like a pizza concept, right? You should have it in less than 30 minutes. the food that you're going to eat. And that's not as crazy as it sounds. And by doing that, you're getting the maximum nutrient density value from the crop that it was able to give you. Now, processed food's a different story, things that need to be processed over time. You know, I am not, at this point, working on transportation infrastructure and design related to the food that I'm creating because I am assuming that it will be point source consumed. Now, again, another avenue for another person that hopefully gets onto one of these farms and then figures out when they need to distribute it. But I would say the maximum benefit of urban farming is the fact that it's grown right where it would be consumed, therefore much more sustainable, and the yield conversation becomes much more interesting related to a biodiversity conversation. And the fact that I can create a lot of diversity in a very short amount of time that a traditional crop manufacturing process could not do. I can respond to market demand in a much more agile way. So seasonality, right? Seasonality is a blessing for me because that means that there is a time in the world when they do not have the things that people may want to have. And you can go into production of that. Blight. Blight in the commercial environment is a blessing to me. When a hackberry tree, which is happening now, has a blight in the world and they all die, which a lot of them have, I can go into hackberry production very quickly and create viable seedlings. See, that's the other thing. These environments are thought of, like the way that you're thinking of it is probably eat fresh, pick fresh. Like you go into this thing, you pick it out and you eat it. However, this has a relationship to traditional agriculture too, or it could. I can produce tiny hackberry trees and then plant them outside. And I can do that much faster than any other commercial process if there is some kind of problem. I can also produce things like protein. So pea protein, legume protein, things that need to be made into new combinatory superfood or new combinatory protein sources. That's where the big companies are interested. They want to know what is their supply line, how stable is that supply line, how sustainable is that supply line? You know, like, so they go into all of those questions. So I think there are a lot of applications. We didn't get much into applications for this. You know, that will address the issue and change the discussion of the value of yield and the value of logistics as it's related to food systems. We've exhausted you all.
Well, if there are no more questions, I would like just to wrap up, you know, just to say a few things that kind of like resonated, you know, on the basis of what you've been, you know, teasing out, you know, during this wonderful evening. And one thing, if we're speaking, one thing is for Caleb, right? It's more like rhetorical thought, you know. If we are thinking about, you know, empathy, you know, kind of like, you know, I would like to kind of like move from empathy towards criticism. But if you're thinking about empathy, and if you're assuming that plants, you know, do have, you know, certain intelligence, right? Further thinking, you know, we can also assume that maybe water also has certain intelligence, right? As there is this saying that water likes to be played with, right? You know, and when we're thinking about the fountains, you know, when we're thinking about different kind of like sprinkles, and in your work, you know, you're using sprinkles, right? So it is also kind of like interesting question, you know, how this, you know, forces, you know, kind of like condition the intelligence of, you know, certain systems. Like in this case, you know, we're speaking about the water, you know, so how the water intelligence is being kind of like, you know, also suppressed or liberated, you know, through the systems. And how does it also affect, you know, relationship with the plants, right? Because we are talking here about, you know, the feedback loop that is happening. And further on, speaking about the criticism, you know, in that respect, you know, recently Skylar's work was featured in the book edited by Peter Weibel called The Molecular Aesthetics, right? And in presenting this book, and the book I think is published also in, by MIT Press and ZKM. In presenting this book, you know, they're quoting also Felix Guattari and the molecular revolution, right? So I'm really kind of like, you know, curious, like further thinking, you know, this relationship between, you know, the revolutionary forms and also forms of the aesthetics, you know, how you're working with the idea of the model and kind of like, you know, mathematical model as it was suggested, you know, how does that feed, you know, into kind of like, you know, this space, you know, of the aesthetics? You know, as we know, that sometimes we are speaking about how beautiful is the code, right? So, in that instance, you know, it would be really interesting, you know, to think in terms of kind of like new, radical, and emerging forms of aesthetics, you know, that may contribute to this process of innovation, right? So, thank you very much, both of you, and thank you all in the audience. And just let me tease out a little bit what is happening next week. On Friday, December 19, we will again gather in this wonderful room at KTU to hear free presentations, free speakers. The lectures will start at 1 p.m. With a professor from Rice University, Timothy Morton, and his lecture, I Believe in Coral. Then it will continue with the presentation by Jeremy Lee, who is designer and artist and also alumni from MIT, from architecture and in fact from the program, visual art program at MIT. And her lecture will inquire precisely the infinity burial suit. That's how it is called. So it will inquire what our bodies are living on this planet and what are the possibilities to actually rethink, you know, the toxins and rethink what we're living. And the third presentation is by the territorial agency that is represented by John Paul Messino and Anne-Sophie Ranskog. And they will tease out the recently developed project that was featured also at Hauskultur and der Welt within the Anthropocene, large investigation, and that is called the Anthropocene Observatory. So welcome you all next Friday, and thank you very much for tonight.